Hi, in this I will be discussing about deformable data, which is an improvement over the data, which was an architecture proposed to use transformer for object detection task. So in detection transformer, what they did is they had a convolutional backbone, and they took the final feature map uh, of the channels, and they flattened it uh, and pass it to the encoder. And in the decoder side, they had 100 queries, set dimensional, and each query was supposed to learn if there was an object in a certain part of the certain region of the object or not. And in the end, they have a bounding box. I'm not going to the intricacies involved in the training, which is actually good, which is actually based on a Hungarian laws and bipartite matching and stuff. So here I will be mostly focusing on what are the problems with the DETR architecture and how deformable DETR is solving them. So the main problems with data architecture was initially the data architecture had difficulty detecting small objects. So they have very bad performance in small objects and very good performance in detecting large objects. So the what the authors of this deformal data found was because why this happened was they are only looking into the last feature layer. So if you have a backbone like this, if you have a backbone of a convolutional backbone like this, so we know, like, we take the input, and say if you get the input from here, if your image was some channels, as it goes down, the channel dimension reduces. So 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 uh, for a pic- pixel here, the receptive field, which means the corresponding patch it is looking into the image, will be much larger. So it will be smaller, it will be smaller for, say, here, and then even the receptive field of the very layer in the beginning will be much smaller. So to detect large objects, what we require is to use all these features across all these layers. But it is a bit difficult for data, because in case of data, they were flattening the features, and say this is 256, say the channel dimension, and this will become 34 into 34, uh, 134 and 134, or so if you were to use all the channel dimensions, then we will have to flatten all of them, and this will correspond to some 23,890 into 56. And so this many queries, and this is the channel dimension. So doing a self attention on this many queries is very expensive. So that is not possible. This is computationally not feasible. So what the authors of deformable, so to detect small objects, we need to look into small feature maps, but we should not have a computational explosion. So what the authors of deformable detector suggested is, they found out a clever way, which we will discuss down, downstream in the blog, to say for each point look into corresponding points across different feature map and some other points in each feature map. So instead of looking into all points in all feature map, uh, just look into some other couple of n number of points, say, across the L levels. So that is only required, because say the point here might not be exactly interested in what is happening here. It might be only interested in what is happening in its region of interest, or around the area. So how the network design helps this uh, in attending all the queries across different feature level, that we will discuss downstream. But this, on a high level, this is how they solve this computation explosion problem. So they detect only a certain number of features across each, they attend. So the key attend, the query attend to, is very less. So that is how they reduce the number of features that we attend to. So the next problem with DETR was long training time. So the training time the DETR requires was very much high. The reason for this can be understood if you look into the attention head of DETR. So if you look into the attention head of DETR, you can see that the attention head is actually trying to focus on the corner of each image. And since it's a full self attention, what happens is we are looking into all the queries, right? So to find out the right queries to look into, it takes too much time to converge. So intuitively, this architecture is preventing that as well, because now we are not attending to all the queries and only to a certain number of queries or keys uh, per query. So here we should be intuitively able to learn the attention faster as well. But how we come up this point should be a clever way, so that we are able to actually learn the right attention and not the wrong attention. So that is how on a top level how deformable data solves the problem with these two things. Now on a top level, the architecture is very much similar to what is there in data. There will be so the architecture is very much similar. So there will be a convolutional backbone, and we will be using uh, C1, say C1, C2, C3, and C4, four layers from this convolutional backbone. Then we will flatten them up, and there will be an encoder, and this encoder, these features will be passed through the encoder, and there will be queries, learnable queries similar to what was happening in DETR, and uh, there will be cross attention happening, and the training is also similar to how it was in DETR. So the key innovation here is, instead of self attention and cross attention happening on a higher number of image features, we will have something called deformable attentions, which we will discuss downstream, so that it helps us to attend to different feature map across different levels. So on a higher level, this is what is happening in DETR. So now we will look into the convolutional backbone. So initially, as I said, so we will have say we will, in the paper they used say the last three layers from a resonant, and then they have a constraint on the last layer, producing a further down sampled feature map. So I didn't use a con layer, so I just produce random shapes of this dimension and corresponding positional embedding of these dimensions. So I didn't also specifically, so the positional implementation of positional embedding can be found here. So this is the same positional embedding as, say for example, in a normal the sign position embedding, but the only difference is here. So for a h cross w, the positional embedding has to give us the information, vertical information and horizontal information. So what they do is, suppose if your embedding is 250, they will have the first 128 will encode the positional embedding along the vertical direction, and the next 128 will be encoding the positional embedding around the horizontal direction. And the how they encode is very much similar to the sine cosine position embedding that we see in the normal the original attention is all you need paper. So here also I'm just giving the random shapes, because that is not what I'm trying to discuss here. We will be trying to discuss deformable attention. And then since all of these are of different shape, you need some one cross one convolution that put them in the embedding dimension of 256. Now we will have everything in embedding dimension of 256, and we will have feature map from all different levels. So we will be able to look into different number of objects. And finally, one more thing that we need to understand here is, so we have four different levels, right? So you have four different levels, and the network should understand, uh, should have an embedding for differentiating four different levels. So this is a learnable embedding of size say 4 comma 256 for each number of level. And how we what we do is we just flatten all the embeddings, all the feature map, and add them up. So this will be from 134 comma 134, and this will be from 67 comma 67, like that. And corresponding level embeddings will be added, positional embedding and level embedding will be added, and the corresponding embedding dimension will be the similar. And we flatten all of them, add them up for feature map as well as for positional embedding, and in the end what we get is a flattened feature and flattened positional embedding which have level embedding also in them. So now we have a 23980 comma 256 which contains from four levels, and uh, the corresponding embeddings also, and the four is the batch size. So the next thing is how the encoder carefully attends. So these many queries are there, so we cannot do a full self attention. So next we will discuss how the deformable attention is happening and helping in solving this computational expression problem.